All right, so here I'm going to talk about some word problems that are still in our arithmetic sequence problems, arithmetic sequence section. So here we've got a person who's making monthly payments, and the first monthly payment is 55, and then 52, and then 49, and then 46, and then 43. And so it's going down by 3. So if I want to think about what the nth term is, maybe I'll call it P. This is payments. The nth term is, well, his first payment was 55. Each payment after that goes down by 3. I can't write 3n because if I write 3n and I try plugging in 1 for the first term, I would be at 55 minus 3. So I go 55 minus 3 times n minus 1. The n minus 1 allows me to deal with the first term being 55, because now plug in 1 and you'll get 3 times 0. If you plug in 2, you'll have 3 times 1. If you plug in 3, you'll have 3 times 2. So that is the nth term. Find the amount of the 12th payment. Well, the 12th payment is just 55 minus 3 times 11. So P12 is just 55 minus 33. So the 12th payment is 22. By the way, it is totally valid to just write out the rest of the numbers. I didn't ask you to do the 107th payment. It's the 12th payment. You could write them all out in between. Determine when Pablo will make his last payment is the next question. So the last payment would be figuring out when the sequence reaches 0. So I would say let's make 0 equal 55 minus 3 times n minus 1. So take away 55 from both sides. Divide by negative 3. 3 doesn't go into 55. What's that decimal? I could probably do it in my head, but I don't want to. So 18.3 repeating is n minus 1. So 19.3 repeating is n. So what that means is that he makes 19 and a third payments. So after 19 payments, he still has a third of a payment left to make. Okay, and so he'll pay that last payment. It's just not going to be a full payment. It would just be a third of a payment left. So I guess you could write that out just like 19 full payments and 1/3 of a payment. And by the way, if you ever take out a loan, buying a car, buying a house, paying off a credit card, whatever it is, you'll see something that's called a payoff schedule or an amortization schedule. You'll notice that like all the payments are the same amount, and then like the very last payment is usually different. And that's this idea right here. You're paying down the same amount every month, so you have like a consistent budget, $3 a month. And then the last payment is just whatever's left over. There's no reason to assume it's going to be a full payment that's left over. And then part D says find the amount of a last payment. Well, we figured out that it's a third. It landed kind of nicely. So a third of a normal payment, a third of $3 is $1. But wait, let's say the numbers were worse. What we could do is use the whole number part here and say that on 19, on P19, we're going to go 55 minus 3 times 19 minus 1. So that's 55 minus 3 times 18, which is 54, which means his last payment is $1, which makes sense. It's a third of the normal payment. So there's that. A little real world connection with making a payment schedule as things go down like that. And that's typically how payments work, although they usually are not arithmetic in their sequences. They're usually geometric in their sequences, but that's a little bit beyond the scope of this video. Okay, the other word problem I was going to do is about a sequoia tree, beautiful tree. So it's 2.6 meters tall in 1998 when it was planted. Then it grows 1.22 meters per year. Well, guess what? I'm going to call this S1 because we're using S for sequoia. And I'm going to call this D because that's how much it changes by. Okay, and actually the textbook asked me to use A1, so gosh darn it, I won't use S for sequoia, I'll just use A. So let's write down a formula. The nth year is going to be what it started at plus what it grows by times n minus 1. Find the height of the tree in 2025. Well, if it was planted in 98, then 2025 is 27 years later. So 27 years later is 2.6 plus 1.22 times 26. That's just something to type in. 2.6 plus 1.22 times 26. Type it in, 34.32. It is a freaking tall tree. Remember, these are meters. So that's well over 100 feet tall at that point. It's a big tree. Part C, the tallest living tree has a height of 84 meters. That's super tall. In what year would the plant in 98 reach this height if it continues to grow at the same rate? So now we're doing a solving thing. We have 84 meters equals 2.6 plus 1.22 n minus 1. Let's take away 2.6. So we have 81.4. Let's divide by 1.22. Let's see, 81.4 divided by 1.22. 66.72. N minus 1, add 1 to that. 67.72 years. That's how long it would take. Of course, trees don't grow at the same rate forever and ever and ever, but uh, still kind of a cute word problem. So thanks for watching. Next video, I'm going to do some arithmetic sums. Comment if anything was confusing, please.